Hello there, I'm back. This is lecture number 3, and we started with introduction to the course and then moved into energy. And remember, there's two things in the universe. So after energy, we have to talk about matter because that's the second thing in the universe. So I'm calling this lecture Important Matters. It's kind of a joke. The readings are in the AP Environmental Science text, Chapter 2, and the Introduction to Environmental Science text, Chapters 3 and 4. I don't know whether you enjoy the chemistry cat that they make these memes out of, but we're talking about matter, so I have a chemistry cat meme that says, you have mass, you take up space, you matter. That's kind of the standard definition of what matter is. Anything that has mass and takes up space. So this is a kind of a joke about you matter. And of course, I'm sitting here telling jokes in my office where there's nobody to laugh, so I told a chemistry joke. No reaction, which is another chemistry joke. Okay, let's get going. All right, a little reminder of where we're coming from. There are only two things in the universe, energy and matter. Last time we talked about energy, and this time we talk about matter. When we're using a systems approach, we need to remind ourselves that energy flows through systems and matter cycles within systems. So in this lecture, we're going to be talking about the cycling of matter. All right? So matter is something that I'm sure was discussed much more in whatever science that you bring with you to Columbia College. So I'm going to do what I like to think of as some review of matter. It may be a little more complicated than you think, but I consider this review. Anyway, as I said just a moment ago, matter is kind of defined as anything that takes up space and has mass. That's a little bit odd because we think of mass as how much something weighs, but how much something weighs depends on where it is. Something weighs a different amount on the moon versus on the Earth because there's less of a gravitational pull. But that something has the same amount of mass in either space. So we kind of have to define what mass is by, where the gravitational pull is. But mass is really the characteristic of something to actually be impacted by gravity. So matter has to be impacted by gravity and it has to take up space. Those are the two things that define it. And because there's only two things in the universe, I like to say in this list that matter is not energy. And they're not really convertible except in a weird quantum kind of situation. The thing that everybody learns in school about matter is that it comes in three states. There's actually a fourth. They talk about it being in a plasma state, but we don't really need that here. So the three states of matter are solid, liquid, and gas. Solid means that the matter we're talking about has a fixed shape and a fixed volume. All right, so we can use those metric system measures in order to kind of describe it and so that it's not going to be changing. Fixed shape, fixed volume. Liquid means fixed volume. We can't change the volume of a liquid, but we can change its shape. It actually takes the shape of whatever container you put it in. All right, so fixed volume. Gas, no fixed volume, no fixed shape. The atoms or molecules or whatever particles we're talking about are kind of free to move and they have very loose bonds with each other. So we're starting to talk a little bit about chemistry because I'm talking about atoms and molecules, and I'll get into that a little bit more deeply. But solid, liquid, gas is important that whenever we're talking about matter, we know which one of these states that it is in because the rules are going to be a little different depending on what state we're talking about. And there's a little description under each one of these pictures. Okay, a little bit more matter review. I would expect that you had seen a picture like this. I'm going to talk about atoms now. If we take matter, solid, liquid, or gas, doesn't matter, and we break it down and break it down and break it down and break it down, the smallest particle that we can break matter down into that still has the properties of that matter is an atom, all right? And atoms are made out of 3 subatomic particles, but if we break an atom down into those subatomic particles, they no longer have the properties of that matter. So we need to understand what an atom is. It's these 3 things. And it's structured with two of these things at the center, and that's called the nucleus of the atom, and one of these things around the outside of that nucleus. Protons and neutrons, we have them right here, they are in the nucleus. And we sort these things out by the charge that they have. Protons carry a positive charge. Neutrons have no charge at all. There's like a little joke where there's a neutron sitting at a bar talking to the bartender, and the neutron says, gets up, starts to leave, says to the bartender, "What do I owe you?" Bartender says, "For you, no charge." All right, so there's a bar joke for neutrons. And then around the outside, we have electrons, and those have a negative charge. So we have a positive charge and a neutral in the nucleus, and then negative around the outside. And in general, these things tend to balance each other out, the positive and the negative. And that's how we understand all the rules about how atoms interact with each other. All right, so let me look at my list here and make sure that I'm getting everything. An atom can't be broken into smaller parts and keep its property. Each atom can be classified as a single element. I didn't use that word yet. An element is a type of atom, like a flavor or a species of atom, and the type is defined by the number of protons. The number of protons in the nucleus determines what type of atom we're talking about. The only other thing I want to say in terms of the atom and getting this structure understood with the nucleus, protons, neutrons, and the electrons on the outside, is that the word nucleus is used to describe an atom, but it's also used to describe a cell. Do not get the cellular nucleus and the atomic nucleus confused. They're not the same thing, not at all. This is not biology right now. This is more chemistry, physics. So atomic nucleus, protons, and neutrons. Let's talk a little bit more about atoms. Okay, still doing some review here. I consider this review. If you got out of high school without seeing this, I'm crying a little bit inside because this is a really important picture here. It is the periodic table of the elements. All of the different types of atoms are in this chart, and they have little abbreviations, and where the atoms are on the chart tells us kind of what some of their properties are. I already told you that the type of atom that we're talking about is determined by the number of protons, and the number of protons changes depending on where we are on this table. For instance, hydrogen has 1 proton. Helium, right here, has 2 protons. Lithium has 3. Beryllium has 4. I think you see the pattern. We're just going to go across and down, and we're going to add protons as we go. These atoms are getting bigger. So up at the top, atoms are smaller. Down at the bottom, atoms are bigger. So we understand that they're all in order depending on the number of protons. And the next thing we need to do is understand why we have different rows, because if we're just going across the rows, we're adding protons. Why do we have different rows? That has to do with the number of electrons, but that's a little complicated, so I need some more language to describe that. Okay, so I made the table a little smaller so I could say a few more things about it, remembering that the number of protons determines the element, that is the atomic number. And even though it's complicated, in most cases in biology, environmental science, we only deal with a small subset of all of these different types of atoms. CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Where are those? They're all up at the top because they're all nice small atoms. Here's hydrogen, and here are carbon, nitrogen, oxygen, phosphorus, and sulfur. You see they're all the same color because they all have the same kinds of characteristics. Okay, let's talk about electrons. Okay, the element is determined by the protons. The electrons are on the outside. They are negatively charged. They have no mass, but they determine where the element is in terms of the rows, because electrons come in sets. All right, we call them shells or orbitals or clouds. They come in sets, and sets can be complete or they can be missing a couple of electrons. And each row is a different set of electrons, and as we move to the right side of the row, we complete the set. of electrons. So helium has a complete set of 2 electrons. Neon has a complete set of 8 electrons on the outside, 2 in the first set, 8 in the next set. So that's 10 electrons altogether, and you see the atomic number there is 10, so the electrons balance out the protons. Balance is a really important issue with all of these atoms. All right, so each row is a set of electrons or a shell of electrons. We'll see some pictures of these, and we're going to be trying to complete these sets in order to make a nice stable atom. If an atom isn't stable, it's more likely to react with another atom. That's going to be mostly about trading electrons to make sure that things feel balanced out. And so that's what we're going to be talking about as we talk about chemical reactions. One more thing here, there's a word that's really important, ions. If an atom is charged, if it has a slight negative or positive charge, because the number of electrons and number of protons are not balanced, we call it an ion. If an atom is 1 electron short, it has a slight positive charge, we call it a cation. If an atom is 1 electron more than it needs to balance out the charges, we call it an anion. It's a negatively charged atom. And ions show up a lot in environmental science when we're trying to track chemicals through systems. Okay, here we are again, a little bit more detail. Again, the atomic number is the number of protons, and the row that we're in is about the set of electrons. So, and the atoms are getting bigger as we go down, and they are getting more stable as we move to the right. If we have the same number of protons, electrons, and neutrons, everything tends to be balanced out. We're not very reactive, but we can have slightly different numbers of neutrons, which does not change the atomic number. It doesn't change what element we're talking about, but it changes the atomic mass, which is another number. It's down here near the bottom. It's basically how much gravity is going to be pulling on these atoms. And if we have a slightly different number of neutrons, we say that this atom is a different isotope of the same element. Okay, isotopes, again, just like ions, very important because we can use them to track atoms through different systems, and we do that a lot in environmental science. So, protons and neutrons in the nucleus, electrons on the outside, protons positive, neutrons neutral, electrons negative, and they are in sets or shells. We're only dealing with small atoms. Ions are about a different number of electrons giving a charge to the atom. Isotopes are about a different number of neutrons giving a different amount of mass to the atom. Whew, that's a lot. Let's move on from the periodic table. Okay, so atoms are all over the table. Over on the right side, they are more stable, and that is kind of a state stability that all matter is leading towards. That would be an entropy thing if you want to bring that back to the energy discussion. And one of the ways that atoms become more stable is to interact with each other with those outer electron bits so that they can kind of pretend that they have a full set of electrons on the outside. So when these atoms react with each other, we call it bonding or reacting. And there are 3 types of bonds that I need you to know about. The first type of bond is a covalent bond, which we call electron sharing. And so atoms are going to be hanging out right next to each other, pretending, each one of them pretending that they both have a full set. So here's hydrogen, which only has 1 electron on the outside, but each hydrogen atom is pretending to be helium because when they're right next to each other, there's 2 electrons buzzing around. So each of the nuclei kind of has access to 2 electrons on the outside. So hydrogen atoms tend to be traveling around with each other because of this electron sharing. That's called a covalent bond. Sometimes covalent bonds are a little bit unequal so that one atom gets to hang on to the electron all the time and the other doesn't get to see it very much. That makes it polar. Here is a water molecule, oxygen and 2 hydrogens, that's H2O. But the oxygen is a little greedy, so it gets more of a negative charge because it hangs on to the shared electrons. and hydrogen doesn't get to see them as much. So each hydrogen atom has a positive charge. So it's still a covalent bond, but it's a polar covalent bond. Okay. The next type of bond is what's called an ionic bond. It's still kind of electron sharing, but really it's kind of a completely unequal sharing where one atom gets to hang on to the electron all the time, and it tends to balance out both of these atoms in terms of filling out the outer electron sets. So here's an example of an ionic bond. It is sodium chloride, which is table salt, and by hanging out together, both of them get to pretend that they have a full set of electrons on the outside, even though normally as an individual atom they do not. So in this case, sodium is on the left and chloride is on the right, and they both look like they have 8 electrons filling the outer shell, so they're really happy together in this ionic, and we call it electron transfer. So covalent is electron sharing, ionic is electron transfer. Those tend to be water-soluble bonds because if we add water, water's got all these weird charges, and so it kind of breaks up this transfer process. One more type of bond, it's called a hydrogen bond, and it's a very weak bond, and here's an example of 2 water molecules sticking to each other simply because one of them's got a little bit of positive charge on this side, the other's got a little bit of negative charge on this side, and opposites attract, so they kind of stick to each other electrostatically, kind of like that static electricity. Very weak, but very important. And so we have these 3 different types of bonds. By the way, a little bit of a funny, there are strong and weak bonds, and here are what I consider some of the stronger and weaker bonds. One more piece of information, and that is sometimes when 2 atoms or 2 molecules interact with each other, energy is released from that interaction, and we call that an exothermic reaction, giving up energy or heat, and sometimes it requires energy to make that reaction happen, so it absorbs heat or absorbs energy, and we call that endothermic. Okay, enough about bonds and reactions. Woo, that was a lot of chemistry class. Let's get back to environmental science. We're talking about environmental systems, and in this case, we're interested in matter and matter cycles within the system. It might get pulled out or pushed in around, but mostly it's cycles, so we need to talk about cycles. CHNOPS are the elements we're concerned about, and those things are right here when we start to talk about the essential chemical cycles. We got water, so that's got hydrogen and oxygen, and then we're going to add carbon, nitrogen, phosphorus, and sulfur. Bam, there we have all of the elements that we need to be concerned about. So let's talk about those. Okay, so this is a little bit of an explanation for why those 6 elements, CHNOPS, why they are so important in environmental systems and living organisms. This is probably the most important lesson in biochemistry that you'll ever learn. Everything that's alive is made up of really big molecules that are made up of slightly smaller molecules. The big molecules are called polymers, and the small molecules are called monomers, and living things all have carbon in all of those molecules, so we say that those are organic. Organic polymers, organic monomers. Water is really important in terms of this polymers and monomers because in order to build a polymer out of a bunch of monomers, we need to take water away. That's called dehydration synthesis. And in order to break down a polymer into monomers, we need to add water, and that's called hydrolysis. But the nice thing is that there are really only 4 types of these big polymers that we need to deal with. And they're the same ones that you see on a nutrition label from something that you're eating. There are carbohydrates, there are lipids, there are proteins, and you probably don't see nucleic acids on a nutrition label. But DNA is a nucleic acid, ATP, if you've heard of that, is a nucleic acid, and it's really important in terms of the way that living organisms function. But over here on the right, we can see that they're all made up of those elements, CHNOPS. and there are different arrangements of them. If we have mostly carbon and water, carbohydrated. So carbohydrates are mostly carbon and water. If we have lipids, it's mostly just hydrogen and carbon. We sometimes call those hydrocarbons. Not carbohydrates, but hydrocarbons. If we have proteins, we're going to toss some nitrogen in there and some sulfur because we arrange these in different ways. So we got the whole, we have all of the elements in the protein, CHNOPS, they're all in there. And then finally, nucleic acids, not quite as much sulfur. But you might have heard about DNA having phosphate groups and nitrogenous bases and sugars. There they all right there. So anyway, those elements are in all of these important molecules. So that's why we need to be able to track them to see whether or not organisms are going to be able to live in an area depending on whether these elements are available. Okay, so the rest of this lecture is going to be about those 5 essential chemical cycles that I had a couple of pictures ago, and the first one was water. We know a lot about water. We're all made up of water. The planet is covered with water, 70% of the earth. It exists in all 3 states, that's solid, liquid, and gas. That would be ice and liquid water and water vapor. No life that we know of is possible without it. That's why there's robots on Mars crawling around looking for evidence of water, because evidence of water would be, yes, there's a possibility that there could be life there. All right, H2O, no big surprise there. We've heard that a bunch of times. We now know that it is a strong covalent bond that holds the atoms together in a water molecule, but there's weak hydrogen bonds that hold 2 water molecules together. Water molecules like to stick to each other, but pretty weakly, which is why you can splash around in water, because it's easy to separate those molecules from each other. It's not easy to separate hydrogen atoms from oxygen atoms. It's just easy to separate the molecules. So water molecules are easily separated, but not broken. Water. Okay, so we will talk more about water later because there's lots of reasons why it's important environmentally. But here is a picture of the water cycle provided by the U.S. Department of the Interior and the U.S. Geologic Survey. It's a system with a box around it, and we have arrows, and chemicals are cycling within this system. Starts in the ocean and evaporates to become vapor. And then it travels in the atmosphere, falls down as rain, flows across the land. Also, the geology of the land itself has a lot of water in it, so we're often looking for how much water is being moved around in all of these different arrows. Pretty cool. Okay, so the next chemical cycle we're talking about is carbon. Carbon is in the second row of the periodic table, so it's a small molecule, but it has 2 sets of electrons. The inner set is just 2, so that's happy. The outer set is 4, so carbon is very reactive. It has a high valence because it could gain electrons to get more stable, or it could lose electrons to get more stable. In either case, it's getting closer to a complete outer shell. So that's why carbon is the atom that all life is built on, because it's really easy to build stuff out of it and then break that stuff back down. It's kind of like having a set of Legos or Tinker Toys that you can build something out of and then break it down and save the parts to build something later on. So carbon, and this gives some of the details about the electrons and protons and neutrons of where carbon is in that second row. Okay, so here is the carbon cycling within the environmental system. There are some things in here you might recognize. There's photosynthesis right here, which is taking carbon out of the atmosphere and putting it into living organisms. There is respiration, which is basically eating carbon and then breathing it out as carbon dioxide, putting it back in the atmosphere. And then there's digging it up, which we'll be talking about a lot in this class, digging it up and burning it, which takes it from a solid state or a liquid state and puts it back in the atmosphere again. Those are the 3 major ways that carbon gets moved around, but they're happening everywhere, and also obviously there's things moving around in the rain, in the water, so the carbon cycle is pretty important. Again, we'll talk about this a lot in this class. Okay, the next chemical cycle is nitrogen. I describe it as the most abundant and useless gas in the Earth's atmosphere. The atmosphere is mostly nitrogen. We breathe it in, we breathe it back out again. We don't use any of it. The only way we get nitrogen is through our food. So it is engaged in ecosystems, and because organisms eat each other, and that's how the nitrogen gets moved around. In fact, in order for nitrogen to get into plants, it needs to be in the soil, and that's why we put nitrogen into the soil when we're fertilizing plants in order to get them to grow better. Nitrogen is in proteins, it is in nucleic acids, it is required for life. There's just a lot of it in the atmosphere that we don't use. Nitrogen is also in the second row of the periodic table. It has one more electron in it. There's 5 on the outside, and so it's a little bit less reactive than carbon. And it does cycle, and we do like to track it through a lot of the different systems on Earth. Okay, so here is the nitrogen cycle, and as you can see, there's a lot of it up here in the atmosphere. There's really only 2 ways it gets out of the atmosphere. One of them is by bacteria, that's this arrow right here, which are able to pull that nitrogen out of the atmosphere and make it part of the soil. And the other is by humans that pull nitrogen out of the atmosphere. That should be a bigger arrow, really, but they pull it out, they make fertilizers out of it, dump it on the ground, and then once it's on the ground, it's all about bacteria. Bacteria, look at all of these bacteria down here doing different things with nitrogen. And then, of course, it becomes available to plants, which then make it available to animals, which then eat each other and die. And so the nitrogen gets cycled around in the soil. And every now and then, bacteria stick it back up into the atmosphere. So it's all about bacteria and then cycling around in the ecosystems, nitrogen. Okay, so the next chemical cycle is phosphorus. Phosphorus is found in DNA. Phosphorus is sometimes found in proteins and some other important organic molecules. One of the most important things that phosphorus does is it makes it possible to build a layer of molecules around a cell, which is the membrane around a cell. You might have heard of the phospholipid membranes around a cell. These red bits right here in this picture are the phosphorus atoms in this phospholipid membrane. The rest of it, the whites and the grays, those are all hydrogens and carbons, because that's the lipid part. Phospholipid. Anyway, phosphorus is a little bit bigger. You can see that it has 3 sets of electrons, 3 electron shells. It doesn't, it's the one thing that we talk about here that isn't really up in the atmosphere at all, because it doesn't form a gaseous form that goes up into the atmosphere. So the cycle looks a little bit different. Okay, so here's the phosphorus cycle, and as I said, there's not much going on up here in the atmosphere. It is released from volcanoes, and then it's released as an aerosol, and then it falls back down and gets involved in what's going on the ground. And what's going on the ground is the food webs, and it's moving around with the water cycle, washing into the ocean, moving around, becoming rock, and then breaking up and becoming soil again. Anyway, it's all on the ground. Phosphorus tends to cycle locally or regionally, not globally, the way those other elements do, because they are part of the atmosphere. Okay, last chemical cycle is sulfur, and sulfur is very important in the structure of proteins. Remember, proteins we see on all those nutrition labels, pretty important, but they're also important in terms of organisms. No proteins, no muscles. No proteins, no hair. Keratin, that hair is made of, is a structural protein, and sulfur determines how curly your hair is because of the bonds that it makes in there. Sulfur is one of the bigger atoms, 16 protons, 16 neutrons, and 3 sets of electrons on the outside. It doesn't really exist in a gaseous state very often, so again, it's one of those local cyclers, and it tends to be cycled on the ground. The only way it gets up into the atmosphere is when we burn fossil fuels. We're burning the remains of old organisms that used to be alive, so we dump sulfur into the atmosphere, which is a bit of a problem because it causes acid rain, sulfuric acid. Anyway, let's look at the cycle. Okay, so here's the cycle. Again, here's burning fossil fuels, putting it up in the atmosphere, making some acid rain, but mostly everything's going on down here. We can get some from volcanoes, and we can get sometimes when things decompose, they dump a little into the atmosphere. But in general, it's cycling around down near the ground. So organisms are getting sulfur from where they're eating and how they're interacting with other organisms. Okay, so my timer is showing that I'm at about 30 minutes, so I'm done. This is just a little bit of a reminder of the periodic table. Remember that the atomic number is the number of protons. The atomic mass, which is this number down here, is protons plus neutrons and how much gravity pulls on them. The row that the element is in is determined by the number of electrons. If we're farther over to the right, we're more stable because the set of electrons is full, and we're primarily concerned with C, H, N, O, P, and S. And we know a little bit about the cycles, but we're going to be revisiting those elements throughout this course because those are the important matters that we're concerned about in environmental science. See you in class.